in this talk, I would like to present results of several works which I did with my collaborators. And in these works, we studied model properties of certain BPS indices, which count black hole states in Calabi-Yau string compactifications. And we didn't just study the properties of these guys, but we actually used them to compute these BPS indices. And this is what I'm going to explain you. But first, let me start from explaining the general setup which we considered and posing the problem which we tried to solve. So let's consider type 2A string theory on a Calabi-Yau threefold. And then, of course, in 4 dimensions, we get effective theory, which is given by n equal to supergravity coupled to some number of vector and hypermultiplets. And in this theory, we can define BPS indices, which count, BPS states with a sign of a given electromagnetic charge. This charge has two B2 plus 2 components, where B2 is the second Betti number of the Calabi-Yau, just because we have B2 plus 1 gauge fields in this theory. So B2 of them come from vector multiplets, and one additional comes from the gravitational multiplet. And of course, each gauge field gives one electric and one magnetic charge. So for me, P0, Pa will be magnetic charges, Qa, Q0 will be electric. And P0 is associated with this graviphoton, and Pa, Qa with the vector fields from vector multiplets. And these BPS indices, they have both physical and mathematical incarnation. Namely, from the physics point of view, as I already mentioned, they count the states of half BPS black holes appearing as solutions of n equal to supergravity. And at the microscopic level, the same black holes can be interpreted as bound states of D6, D4, D2, D0 branes, wrapping respectively 6, 4, 2, and 0-dimensional cycles on the Calabi-Yau threefold. And what's nice is that these charge components, they precisely correspond to these d brane charges. So P0 is D6 brane charge, for example, Qa is D2 brane charge, and so on. And on the mathematical side of the problem, so these BPS indices, they have been conjectured to coincide with the so-called generalized Donaldson-Thomas invariance of the Calabi-Yau. And for mathematicians, it's a really great challenge to compute these guys. And probably at this workshop, I shouldn't explain why these BPS indices are important from the physics point of view, but okay, let me mention just that, of course, they give entropy of black holes, which we're all very interested in, and also they appear as they parameterize the non-perturbative contributions to the effective action, for example. So therefore, they are really important. And if we consider it a non-compact Calabi-Yau, then we could use many different techniques to compute these BPS indices, such as localization, quivers, relation to some topological theories. But once we are not on a compact Calabi-Yau, most of these techniques just don't work. And it's really a very hard problem to compute these BPS indices. But nevertheless, let's try. So I will actually consider mostly concentrating this talk on a certain subset of these BPS indices, which correspond to D4, D2, D0 bound states. So in other words, I put my D6 brane charge equal to 0. And the corresponding DT invariant is called rank 0 DT invariant. As you can get, the rank here simply means the value of the D6 brane charge. And this particular subset, D4, D2, D0, they possess some nice, the so-called spectral flow symmetry, which allows to little bit reduce the dependence on the charges. So the BPS index will still depend on the full D4 brane charge. Also, there will be dependence on D0 brane charge, or more precisely on its kind of shifted version, which I denote by Q0 hat, and which stays invariant under this spectral flow symmetry. But what is important is that instead of the full dependence on D2 brane charge, there will be dependence just on the so-called residue class. And it's important because this guy takes only a finite number of values. And namely, it takes this number is equal to the determinant of quadratic form constructed from the intersection numbers of the Calabi-Yau and the D4 brane charge. And therefore, I can denote my BPS index as index labeled by D4 brane charge, this residue class, and it depends on this invariant D0 brane charge. And after that, I can sum over this Q0 hat and get a generating function of these guys, which is labeled by D4 brane charge and this residue class mu. And you can interpret this residue class mu as a kind of vector index. So in other words, this generating function HP will be a vector valued object. And the number of components is given by this determinant of kappa AB. Just one important comment is that actually we consider generating functions not of the original integer valued BPS indices, but of the rational version. And this is because it's expected that once you consider generating functions of these rational values, then these generating functions will possess nice modular properties. I'll explain you later where these properties come from and how they look like precisely. But at this point, let's just consider the most simple example where D4 brane wraps an irreducible divisor.
Hey, can I ask you a question? Sorry, Sergey. Yeah. What is Q0 max? How does it arise?
Yeah, okay, indeed, it's important for the being able to define this generating function that Q0 hat is bounded from above, and it comes from the so-called Bogomolov bound. So it's a general mathematical property of DT invariants that they vanish if this bound is violated. So it was proven by mathematicians long ago, and it's well established. So let's return to our simple example of a reducible divisor, which means that we put our D4 brane on a 4 cycle, which cannot be decomposed as a sum of other 4 cycles. And in this case, it has been argued already many years ago by Maldacen, Strominger, and Witten that this generating function must be a weakly holomorphic vector-valued modular form of this particular weight determined by the second Betti number. So let me explain what these words mean. So weakly holomorphic just means that when I expand my generating function in a Laurent series in Q, so which is an exponential of 2 pi tau, then my series will have a part with negative powers of Q. There will be a finite number of such terms, but they must be present. So in other words, this n mean is less than 0. Or in other words, Q0 max is larger than 0 here. And then vector value just means that we have this vectorial index mu, and modular of this weight means that under the standard modular transformations, we get this standard factor c tau plus d to the power of the weight. And here we get just, well, since our function is vector valued, we get a rotated version of this guy, where this matrix mu is called multiplier system, and it's well known. So it's some fixed representation of a finite dimensional representation of SL to Z.
Sorry, question.
Yeah.
Is the mu in HP in mu the same as the residue class mu? Or
yes, yeah, it's the same mu.
So I sort of lost a bit of intuition. Can you say something more about the residue class, please? Because my internet got stuck.
So where it comes from?
Yeah.
Well, there is the spectral flow symmetry, which allows, which says that, roughly speaking, your BPS index is invariant under certain shifts of the charge vector. And these shifts allow to essentially remove the D2 branch charge, but not completely. So some information about it remains. And then because it turns out that this spectral flow so the D2 branch charge lives in H2 and the spectral flow parameter lives in H4.
So
And
it lives in...
if these two lattices are not the same, then you cannot completely remove the D2 branch charge.
So it's H2 of the Calabi-Yau manifold.
Yes, yeah,
Okay.
yeah, of course, yes. So it's just if your H4 is sorry, H2 is your lattice, then the no, sorry, H4 is your lattice, then this is the standard factor dual lattice divided by the original lattice.
And mu
So
is
mu
then
is an element
runs...
of this residue group.
Okay, and then the cardinality of this residue group is then just the cardinality of H4 minus, sorry, the rank of H4 minus the rank of H2, or?
No. You have to compute the determinant of the quadratic form.
Okay.
Assigned to your lattice, and the claim is that the cardinality of this residue group is equal to the determinant of this quadratic form.
I see. So the determinant of the quadratic form is 1 if it's self-dual? So you're not taking self-dual quadratic forms, or?
Well, I can consider also the case where determinant of this quadratic form is equal to 1. But for example, let's consider one-dimensional case. Yeah, okay, this is the most simple one. Namely, this is what I will consider in the following. Namely, when the B2 is equal to 1. So 1 Keller modulus. Then this quadratic form is just a number. So it's kappa times P, D4 branch charge. So you see, so you can get determinant equal 1, but for this you need to take Calabi-Yau with intersection number equal to 1, and D4 branch charge also is equal to 1. So it's a very, very special case.
Okay. And just the quadratic form that you write out, it's in how many variables now?
What do you mean?
So is it binary quadratic? Is it ternary quadratic? It's some... so A's... sorry, okay, no, sorry, got it.
runs from 1 to B2.
1 to
B2
B2,
is the
okay.
second batch number.
Okay, yeah. Sorry, thank you.
Okay, so we consider this simple example, namely, there is a claim that generating function for irreducible divisors must be a weakly holomorphic vector-valued model form. And there is a beautiful fact that the space of weakly holomorphic model forms is finite dimensional. And moreover, this dimension is bounded from above by the number of polar terms, namely those terms which in this series have negative power of Q. And this means that if you somehow manage to compute the polar coefficients, or the coefficients of these polar terms, then you can restore the full generating function. So just if you find finite number of coefficients, you can get the full function which contains information about infinitely many invariants. And precisely this, we realized this program 2 years ago with Sahelov, Isbach, Albrecht, Klem, Boris Pelin, Torsten Szymanek, for a family of one parameter Calabi-Yaus, and namely we did it in kind of well, one can say in a consistent way, in the sense that we developed certain procedure how this can be done. So let me briefly explain how it works. So we started with the topological string theory defined on our Calabi-Yau manifold, and as you know, this the partition function of this theory is captured by Gopa-Kumar-Vafu invariance. So if you know this partition function, you know this GV invariance. And there is a way to actually find this topological string partition function by the so-called direct integration method, which is, roughly speaking, you solve the holomorphic anomaly equation for the partition function, impose certain boundary conditions which allow to fix the holomorphic ambiguity. In this way, you find GV invariance genus by genus. Once you know GV invariance, you can apply the so-called MNOP formula due to Maulik, Nekrasov, Okunikov, and Podkharipande, which allows to compute from GV invariance rank 1 DT invariance. In our terms, these are D6, D2, D0 BPS indices. And then Sergey derived some nice wall-crossing relations which allow to compute from this rank 1 DT invariance our rank 0 DT invariance. And following this procedure, we managed to compute all polar coefficients for several Calabi-Yau threefolds, compact Calabi-Yau threefolds. And this way, we get precise expressions for the generating functions of our rank 0 DT invariance. And at this point, you can actually go back, and because now you know infinitely many rank 0 DT invariants, just using the same wall-crossing relations, you get rank 1 DT invariants, and you can derive new GV invariants. And this is very important because the direct integration method is actually, it cannot go up to arbitrary genus, because the number of known boundary conditions for fixing the holomorphic ambiguity of topological string grows slower than the number of required boundary conditions to fix this ambiguity completely. So at some point, you are just stuck, and you don't have enough boundary conditions to solve topological string. And our procedure actually allows to get new boundary
Time
conditions.
left, 7 minutes. What is this?
Sorry?
It's the amount of
Yes.
time you can stream on YouTube.
Can you continue?
No, 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 no. No, no.
Great.
I think it's not on the chat. It's upstairs on the bar. It says next to the YouTube blinking link. It's saying time left 6 minutes.
And should I stop? Oh.
I don't know. Sorry. Maybe just give them time to figure out what's going on.
Seems like YouTube doesn't work.
It's until 7 p.m. Why is it giving me the stupid warning?
Gabriel, can I continue? Or...
Sorry.
Yeah, I think you can continue, Sergey.
Yes, I think you can continue, Sergey.
Okay.
Yes, sorry, we have an issue here, a Zoom issue. Please go on.
Okay. Okay, so where was it? Yeah, just that this procedure allows to compute additional boundary conditions for topological string, and in this way we can overcome the limitations of the direct integration method. So this is all nice, but the next natural question: can we generalize this to arbitrary divisors, arbitrary de Forbin charge? And it is this question which I would like to address in this talk. So this is the plan. So first, I will explain you the origin of modular properties, and you will see that for more complicated cases, they're also more complicated, namely there will be certain modular anomaly appearing. And then I will concentrate on the simplest non-trivial case, which corresponds to mock modularity, where we can solve the modular anomaly, then we can find the corresponding polar terms and find precise results for BPS indices. In the second part of my talk, I wanted to consider even more complicated case of kind of arbitrary de Forbin charge, where we cannot still find the polar terms and the corresponding BPS indices, but at least I'll show you how one can solve the modular anomaly in such situation. Okay, so first, let me explain why these generating functions should possess any modular properties at all. Well, you remember we are considering type 2A in the Calabi-Yau, which is the same as M theory in the Calabi-Yau times the circle. Let's compactify this setup on an additional circle. Of course, then we go to 3 dimensions. And in 3 dimensions, our effective theory can always be reformulated as certain supersymmetric nonlinear sigma model with some target space, which I call M. And now you see that in the M theory setup, we have the product of 2 circles, which is torus, and hence we must have the modular group SL to Z in the game. And indeed, one can show that this target space must carry an isometric action of this modular group. And the same conclusion you can get if you work in the T-dual setup. So you do T-duality along this circle S1. So you find yourself in type 2B, and in type 2B there is S-duality. And then this target space M appears as a hypermultiplet modular space and should carry the same isometric action of S-duality. Now, we're considering D4 branes wrapped on a 4 cycle. So since D4 brane has 5-dimensional volume, walled volume, this leaves still 1 dimension uncompactified, and let's also compactify it on this additional circle S1. So then all dimensions are compactified, and we get, from space-time point of view, kind of point-like object, which of course can be interpreted as an instanton. And these instantons, they do affect the theory, namely they affect the metric on this target space M. So they induce certain instanton corrections to the metric tensor. And moreover, these instanton corrections, as already mentioned in the introductions, they are weighted by the BPS indices, omega or gamma. But the good news is that we know how to compute all these instanton corrections. So we did it 15 years ago already. So there is kind of twistorial construction of a full non-perturbative metric on this target space M. So you see, what do we have? We have a metric which depends on these BPS indices through the instanton corrections, and on the other hand, must carry an isometric action of SL to Z. Of course, this cannot happen for arbitrary BPS indices, and SL to Z invariance imposes certain restrictions on them, or more precisely on the generating functions. And what is remarkable is that actually one can derive these constraints explicitly. And this is what I'm showing on the next slide, namely that these constraints can be formulated in the following way. They require that this particular combination of the generating functions must be a modular form of the same weight which we had before. So how this combination looks like? So you see, you have just the original generating function plus certain correction term. And in this correction term, you decompose the D4 brane charge into some other charges, which all must be positive. And so this is equivalent to kind of having a bound state. So you sum of all possible bound states, and we have a product of generation function corresponding to constituents, and we have certain non-holomorphic function in front. The important point is that we know how these functions look like, but I will not show the explicit expressions because they are kind of complicated and it will require 15 minutes to explain how they look like. Just let me say in words that there are some non-holomorphic indefinite theta series with kernels constructed from some type of special functions, which are called generalized error functions. And of course, since here we have a sum of constituents, the upper bound for this sum is just the number of reducible components which our divisor has. And in the following, I will denote this number by small r. So what this constraint means is that well, as we already know, if our divisor is irreducible, then this, if it's irreducible, then this r is equal to 1, so this term is absent, and this is equivalent to the requirement that our generating function is modular. But if it is reducible, then there is this term, which is non-trivial, and we see that our function must have a modular anomaly, which is cancelled by this additional term. And the function which is modular, this h hat, is called modular completion. And mathematically, all this means that our generating functions are the so-called high-depth mock modular forms. So let me briefly explain again what this word mock means. Well, as you probably all know, mock modular forms have been introduced by Ramanujan, but the general theory was developed just in 2002 by Sander Zwegers, and according to this modern understanding, mock modular form is a holomorphic function which has a modular anomaly, but this modular anomaly is fixed by another modular term, which is called shadow, and has such a form that this particular combination turns out to transform as a true modular form. And again, it's called non-holomorphic completion. So either you have a holomorphic function, but which is not modular, or you have a non-holomorphic function which is modular. Well, but this definition is kind of restrictive, and in physics applications, actually, more often we see the so-called mixed mock modular forms. The difference is that in this case, the shadow is a product of a holomorphic and anti-holomorphic modular forms. Or you can have even some of such products. And now, if you want to define a high depth, then you go by iteration. So depth 0 corresponds to the usual modular form, depth 1 to the usual mixed mock modular form, and then depth n is such a holomorphic function whose modular anomaly is controlled by depth n-1 mock modular form. Okay, so now, well, from now on, let me restrict to just one modulus Calabi-Yau's. So it means P2 equal to 1, and since in this case, the de Forbrin charge is equal to the degree of reducibility, I will use this small r instead of p. And let's consider the most, well, the simplest non-trivial case, namely when r is equal to 2, which corresponds to the case where my generating function is a mixed mock modular form of weight minus 3/2. And then my, well, the equation which I showed on the previous slide, if you take just anti-holomorphic derivative of that equation, well, it's equivalent to this simple holomorphic anomaly equation for the completion of my generating function. And you see that the completion is essentially given by the product of two functions for the charge equal to 1, just because 1 plus 1 is equal to 2. And there is a coefficient in front, which is just a complex conjugation of very simple theta series. And so this is the requirement of modularity in this case. And the question, can we find generating functions which satisfy this property? Well, the problem compared to the previous case of irreducible divisors, that there you remember, if you compute polar terms, you fix completely the function. Here, this is not true anymore, because there is this modular anomaly. And for mixed mock modular forms, polar terms do not fix the function uniquely. But they do this if you first solve the modular anomaly. Namely, you can proceed in two steps like this. So first, you find just any solution of this modular anomaly equation. So any mock modular form whose completion satisfies this holomorphic anomaly. Of course, you can still add to this solution any pure modular form. And then the idea is that you fix this ambiguity by computing the polar terms, because if you computed the polar terms of H2, this function is known, so you know also the polar terms of these guys and or this modular function, and you can fix it uniquely. So we have to do these two steps: first solve the modular anomaly, and then compute polar terms. So let's do it. So in this particular case, well, there is a natural ansatz for solving this modular anomaly equation. Just let's choose H2 to look like this. So you see it mimics the form of this expression. And then it's easy to derive that the modular anomaly requires that this new function, capital G, must be already usual mock modular form, not mixed one, just the usual mock modular form with the shadow given by just this theta series, which you saw here. And it turns out that precisely this problem has been considered by Dabholkar, Murthy, and Zagier in their famous paper, where they first discovered mock modular forms in the context of black holes in string theory. Well, they considered black holes in n=4 compactifications of string theory, but the mathematical problem which they solved was actually exactly the same. Or more precisely, they were interested in mock modular forms with shadow given by this theta series, but they imposed an additional property that the Fourier coefficients of their mock modular forms have the so-called slowest growth. We do not care at all about this slowest growth property, but we can just borrow the solution. So they found some solution of our problem, and any solution would work for us. So let's just take it. And here I just reminded how this solution looks like. So they constructed this solution starting from a certain set of, one can call them seed functions, which you have to introduce at each integer such that its Möbius function is equal to 1, which means that this integer is square free with even number of prime factors. So it's 1, 6, 10, 14, and so on. So they computed these functions. So they know how they look like. And then you just apply to these functions certain family of Hecke-like operators, which I don't specify. You can find them in their paper. So in other words, we know how to construct our functions capital G and hence the solutions of the modular anomaly. Just let me mention this point that among these functions, the first one, Q1, is really special because it's one of the most standard objects in the theory of mock modular forms. So the generating functions of the Hurwitz class numbers. And it's also is known to coincide with the normalized generating function, the so-called SU2 Vafa-Witten invariance on CP2. So probably you know that there is such a topological theory, which is called Vafa-Witten theory. It can be formulated on, essentially any complex surface. It has a gauge group, and in this case, you just take the gauge group to be SU2 and the surface to be CP2. And the partition function of this theory counts certain topological invariants, which are called Vafa-Witten invariants, and the generating function precisely turns out to coincide with this function Q1. And it's very well known, and you see that it's already just this single function already enough to capture all results for where the intersection number of the Calabi-Yau is a power of a prime number. So all solutions of the anomaly equations just captured by this single function. And at this point, once we have a solution of modular anomaly, it remains just to compute polar terms. And we do this in the same way as we did it in the reducible case, namely using wall crossing. So let me recall you at this fact what this means. So first of all, wall crossing is a phenomenon which says that BPS indices are not constant throughout the modular space, but they jump across certain walls of marginal stability. Just because our BPS indices count not only single-centered black holes, but also their bound states. And the bound state can be stable or unstable depending on parameters. So once you cross a wall of marginal stability, some stable bound state can become unstable and stops contributing to the index. This is why the index changes.
Sorry,
yeah.
Quick question. Did you say that the intersection number should be precisely a prime power, or does it have to be non-square free?
No, it can be, so to be, for solution of the modular anomaly to be captured by this generating function of Hurwitz class numbers, it's enough that it's a power of a prime number.
Okay, so it should be like 3 to the 5, 3 to the 6, but not 3 times 5.
Yeah, exactly. Okay. Yes. Okay. And returning to wall crossing, so whether bound state is stable or not stable is determined by the so-called stability condition, which is captured by the central charge function, which is a linear combination of charge components. And the coefficients are given by Kähler moduli and the first derivatives of the holomorphic prepotential, which is itself a function of the Kähler moduli. Okay, how wall crossing can help? Well, in non-compact situation, for non-compact Calabi-Yauss, typically what happens is that you have some distinguished chamber in the modular space where the BPS spectrum is very simple. Then what you do is you compute BPS spectrum there, and then apply very universal wall crossing formulas to compute it in the chamber which we're really interested in. And typically this is the large volume chamber. Unfortunately, for compact Calabi-Yauss, there is no chamber with simple BPS spectrum. This is really the problem of the compact case. So it seems like wall crossing cannot help. But here mathematicians come to rescue us, because what they suggested is to do the following. Let's just drop the condition that f lambdas are fixed functions of the Kähler moduli, and let's consider them to be just independent parameters. So like this, you consider, you enlarge your space of stability conditions. It becomes non-physical, but that's fine. Mathematically, it's well defined. And it turns out that in this large space of stability conditions, there is some distinguished one sitting somewhere on the boundary of the whole space, such that somewhere here, there is a chamber where, well, not all, but at least some of the BPS indices can vanish. And then the idea is that you start in this chamber and you just go to the large volume chamber, where this strange new mathematical stability condition essentially coincides with the physical one. In this way, you can actually derive the BPS indices which we are interested in. And this is what Saheila-Fisbach has done. And as a result, she obtained an explicit formula expressing rank 0 DT invariance in terms of rank 1 DT invariance. And those, as I explained in the introduction, can be computed starting from GV invariance using Komeno-P formula. So it seems like everything is fine, but the problem is that typically we need to know GV invariance of a very large genus. And for most of the Calabi-Yauss, unfortunately, we don't have this knowledge. Fortunately, for two Calabi-Yauss, we managed to compute sufficiently many GV invariants, and as a result, we were able to fix all polar terms in our generating functions, and as a result, to compute them explicitly. So these two Calabi-Yauss are the so-called decantic and octic. Let me just flash very briefly the results for the simplest one, which is decantic, which has the intersection number equal to 1. And here I presented two results. So for generating functions of charge 1 and charge 2. So in charge 1, this is just a pure modular form, as it should be. And so you see it's just fixed in terms of Eisenstein series in the Dekind eta function. And you can expand it and you get some series, and there are just two polar terms here, and well, everything works perfectly. And for charge 2, you already have some mock modular form. So the first two lines is a pure modular form. So, well, you see some crazy coefficients, but this is just, it's expressed in some essentially random basis constructed from Eisenstein series in this theta series. And the most important term is actually the last one in red. And you see it's fixed in terms of generating function of Hurwitz class numbers. And it is this term which is responsible for the mock behavior of this generating function. And for charge 2, it already has two components. So again, you can do expansion and you find precise, well, coefficients. So expansions, you can compute all the coefficients in this expansion. You see that some of the terms are rational, because you remember we're computing rational invariants and not integer ones. And again, here I denoted by blue the polar terms. So you see there are already 7 on them. But we computed using wall crossing not only these polar terms, but also some other terms. And it was really remarkable when you saw that these terms, coming out from the wall crossing calculation precisely coincide with the expansion of this modular mock modular function. So this provides a really very non-trivial test of S-duality of string theory. And I should say that from the mathematical point of view, there is no so far any explanation of this mock modularity. So it's a prediction of physics, but which works very beautifully.
Sergey, can I ask a question here?
Sure.
So the Hurwitz class number generating series there, could you remind me, was this now something you got from the anomaly equation, or how did you discover that it's precisely the Hurwitz class number appearing there in H2?
Well, we just found that the anomaly equation which our functions should satisfy is precisely the same anomaly equation which is satisfied by this function, by this H mu.
For this particular Calabi-Yau?
Yes. Well, it's all this once you have kappa equal 1.
Okay, yeah, right.
If you have, for example, kappa equal 3, it will also be fixed in terms of this function h mu, but you have to apply certain Hecke-like operators to it.
Right, okay.
And if it's, for example, 6 or, I don't know, 14, then other functions enter the game also.
Thanks.
Okay, so this is all what I wanted to tell you about this case of r equal 2. And now, well, in the second half of my talk, I wanted to explain you what happens if we try to solve the most general case. Namely, we want to consider arbitrary de Forbrin charge. Well, and the idea is that we proceed with the same two-step strategy. So first, we want to find just a mock model form of depth r minus 1, which satisfies this anomaly equation. And then we will fix the modular ambiguity by computing the polar terms. So the same strategy. But you see that computing the polar terms is hard, so we don't want to do this at this point, but still we can ask, can we solve the modular anomaly for arbitrary charge? So it is this question which we addressed with my PhD student Khalil Bendrix recently. And immediately you can discover that you have a problem if you formulate the problem like this. The problem is that this equation, you see, depends on full generating functions for lower charges. And if you didn't fix them completely, namely you still have this unknown piece, these unknowns penetrate into your equation. So you have, so how can you solve an equation which involves unknown functions? Well, the idea, okay, you don't solve it exactly, but you can still parameterize the solution in terms of these unknown functions. So our strategy is the following. We produce the following ansatz for this anomalous piece of our generating function. So the structure of this sum is exactly the same as the structure of this anomaly equation. Just instead of h, you put these unknown pieces, but which must be pure model forms, no anomalies. And then you have, you introduce certain new functions, which we call anomalous coefficients. And the whole problem now is to find what these functions are. And how we restrict them? Well, the idea is that this function must satisfy this anomaly equation. And this imposes certain conditions on these functions g, these anomalous coefficients, and the conditions, they're actually very similar to what we just had before. Namely, that these functions must be again certain high depth mock model form, where depth now is fixed by the number of charges on which they depend. And again, the modular anomaly equation can be formulated as an expression for their completion. Just what changes is the structure of this equation. So let me explain how what is the structure here. So the sum here can be represented as a sum of the trees of depth 2, which have n leaves, and you attach the charges Ri to the leaves. And then what you do, you also assign charges S, which are sums to these intermediate vertices, and they are given by just sums of charges of their children. And then you assign also a function G evaluated for these charges to each vertex, and the function R depending on charges S to the root vertex. And then each tree gives a term in this equation, which is obtained by taking the product over all the factors associated to these red vertices and multiplied by this function R associated to the root vertex. And there is also kind of normalization condition. So if my function depends just on one charge, then by definition, I say that this is just a Kronecker symbol. So for example, this factor will be assigned to this particular vertex. So let me give you examples of the anomaly equations which appear on our anomalous coefficients. So for example, for charge 2, well, this is very simple equation. Sorry, not for charge 2, for two charges. So when there are two charges, R1 and R2. And for three charges, well, you see there are three possible trees which we can consider. So this tree corresponds to this term. This tree corresponds to this term because all factors here corresponds to deltas like this. And finally, there are two trees of this form which are related by mirror symmetry. This explains the coefficient 2 here. And you see that there is one factor of R and one factor of G corresponding to this vertex, whereas here it is the factor is delta. So these are the equations which we now need to solve somehow. And I should emphasize that we are interested in any solution of this equation. So we don't need to fix the modular ambiguity. Any solution would work. So let's again return to the simplest case of two charges. So this is the equation which we need to solve. And the only information to find the solution which we need is that the anti-holomorphic derivative of this function R is proportional to the same theta series which we had before. Just the difference is that now the parameter here is not the intersection number of the Calabi-Yau kappa, but this kind of effective parameter which is proportional to kappa but also depends on charges R1 and R2. But we already had precisely this problem before. And we know that its solution is produced by Dabolkar, Murti, and Zaghian, these mock model forms of optimal growth. So we just take it the same solution as before, just again without instead of kappa, we have this effective parameter kappa 0. And so you immediately in 1 minute we get an infinite set of solutions. You see, it's very simple. Now let's consider a special case of this situation where all parameters are equal to 1, so that this effective parameter is also equal to 1. And as I mentioned before, in this case, the solution is just generating function of Hurwitz class numbers. And this is the same as normalized generating function of SU2 Wafavit invariance on CP2. All this I already explained before. And now I would like to claim that this is actually not an accident, but it's a special case of a more general situation. Namely, let's consider another special case where all charges in my function are equal to 1. And also the intersection number of the Calabi-Yau is equal to 1. But now I can have arbitrary number of charges. So let's say n. And then one can show that the corresponding anomaly equation is precisely the same as the anomaly equation for the normalized generating function of SUN Wafaviten invariance on the same manifold CP2. Since the equations are the same, we can also take the solutions to be the same. And this is what we do. So we just claim that this particular set of functions can be taken like this. So again, we obtain in this way another infinite set of solutions. So we have kind of two, one can say, orthogonal sets of solutions. So arbitrary two charges or arbitrary number of charges, but all equal to 1. So after that, it's kind of natural try to something in between. So generalize these two infinite sets. And we tried this with Khalil a lot, but we failed. So we could not generalize any of these sets to any other case. And therefore, at this point, we tried a very different strategy, namely the one which relies on indefinite theta series. And I would like to claim that proceeding this way, we actually succeeded to find solution in the most general case. So using this indefinite theta series, one can find all these anomalous coefficients for arbitrary Calabi-Yaus, arbitrary, with B2 equal 1, but otherwise arbitrary intersection number and arbitrary sets of charges. So since the solution is based on the indefinite theta series, let me explain you a few facts about these guys. So how do you construct them? Well, usually theta series is constructed as a sum of a lattice of the standard parameter q, which is exponential of 2 pi I tau, to the power of quadratic form evaluated on the vector running over the lattice. And the whole point is that for indefinite theta series, you take this quadratic form to be of indefinite signatures. So some number of pluses, some number of minuses, or in other words, there is a positive definite part and negative definite part. But if you just write sum like this, it will be divergent. So your theta series is not well defined. So you must make it convergent somehow. So by inserting certain kernel of the theta series. And there are essentially two standard ways to achieve convergence. Well, it seems like the Zoom meeting will finish again in 10 minutes.
Well, this is very strange. So Abiram, can you take over? This is very strange.
So so can I suggest, I'm going to send everyone a Zoom link right now. So please copy that and paste it and go on that one. So give me a sec.
Yeah, I'm very sorry for this, Sergey. I have no idea what's happening here. I'm on an institutional account. There should not be any such restriction.
I don't
know. Can you send me by email, because I don't see chat.
Okay, I'll send you by email, and I will send everyone by chat first. So please leave only once you've got it. So give me a second. Sorry. Copy notation and okay. So I'm sending the new invite to everyone in the meeting. So please, oops, sorry. Give me a sec. Okay, and Sergey, I will send it to you by email.
Yeah,
so
thanks.
Please go on that Zoom link.
Okay, so let me continue before it stops. Okay, so two ways to achieve convergence for indefinite theta series. One way is just very stupid. You just insert a damping factor, which ensures that along these dangerous negative directions, you have an exponential decay. So you just introduce exponential of this minus q minus. Well, and this way is actually good in the sense that it produces something which is modular. So you get a modular theta series. It's called Siegel theta series. But the problem is that it's non-holomorphic. Well, you don't see tau here, but actually you see in the kernel there is tau too. So when you substitute into instead of x here, you get exponential of minus 2 pi tau 2 q minus. And tau 2 is imaginary part of tau, so you get something which is non-holomorphic. And you may not like it. So there is another way which preserves holomorphicity, and for this you insert a product of differences of sign functions. And if you choose these vectors vi in a clever way, then you can ensure that along these dangerous negative directions on your lattice, where the quadratic form is negative definite, this kernel is actually zero. And then there is no problem. So very good. So we get some holomorphic theta series, but the problem now that it's not modular. And because the signs spoil modularity. And this is the standard situation of mock modular forms, and actually these indefinite depth series, one can say that they are standard examples of high depth mock modular forms, where the depth is equal to the number of negative directions. And at this point, you can ask the following question. So we have these mock modular forms. How do we construct their completions? Well, there is a very general recipe how to do it. It's very simple, actually. Just expand this product of differences of signs, so you get sum of product of sign functions of this type, and just replace each product of n sign functions by the so-called generalized term functions of rank n, which is nothing but convolution of this product of signs with a Gaussian kernel. And the claim is that if you do this, you find something which will be, of course, non-holomorphic because of this, again, square root of tau 2, but will be modular. And I also claim that precisely these guys, they appear as building blocks of the functions which appear in our modular anomaly equation. Okay, so let me now show how this indefinite depth series and what I just explained to you allow to solve our anomaly equations. So again, let's return to the simplest case of two charges. So this is our anomaly equations, and our function R, well, roughly speaking, looks like this. So it's an indefinite depth series with one negative direction, and the kernel given by this, well, this is nothing else but the usual error function minus sign. This difference is actually complementary error function, which is known to be exponentially suppressed. So in a sense, this is an example of this first way of making indefinite theta series convergent. But okay, so what we want in the end to get something modular. So let's choose our function g to be also this indefinite theta series, but with a kernel such that the sum of two kernels is written only in terms of error functions. This is our recipe for modularity, yeah? As I explained on the previous slide. So here, what spoils modularity is this sign. So let's just put this sign so that this sign is cancelled. But the problem, if you have just one sign, it does not provide convergence. To have something convergent, you have to have a difference of two sign functions. So we must insert a second sign. But this sign would spoil modularity. And we cannot replace it by error function because our function must be holomorphic. But fortunately, if the vector W, which defines this sign function here, is a null vector belonging to the lattice, then it actually does not spoil the modularity. Why? Because you see, the argument of the error function is a normalized scalar product. And if the norm of the vector is 0, so the argument of the error function becomes infinite and it reduces to a sign function. So in other words, the signs of null vectors don't need to be completed. They already ensure modularity. So very good. So we found a solution of our problem. But actually, not yet, because we need a null vector. But the lattice, which appears in our case, is just one-dimensional lattice. And one-dimensional lattice does not have any null vectors. And here we can do a nice mathematical trick, which still allows to produce a solution. What we do, we multiply our original equation by some factors, by some number of by Jacobi theta series, and denote so g multiplied by this theta denote as a new unknown function g check. And as a result, we get a new anomaly equation for this g check, which also now depends on additional complex parameters z1 and z2. But the point is that the multiplication by Jacobi theta series essentially, kind of effectively enlarges our lattice, extended. So each factor of Jacobi theta series extends the lattice by additional one dimension. And as a result, you get a new lattice, and a new lattice, you already have a null vector. And you can write a solution, and then finding solution on the extended lattice, you can return to your original problem. And this actually procedure works for not only for two charges, but for arbitrary number of charges. So the idea is that you multiply by some number of Jacobi theta series, this extends the lattice, produces new anomaly equations for new functions g check. You solve this new anomaly equation and then return to the solution of the original problem by applying certain modular derivatives and putting all additional complex parameters to 0. So this is the procedure which one can follow. Well, seems like we're almost done, but again, not yet, because it turns out that to actually realize this problem, we need to kind of do another extension of our problem and introduce the so-called refinement parameter, which physically corresponds to switching on the so-called omega background. And then in the presence of these parameters, our functions will now become not usual modular forms, but we should require them to be the so-called mock Jacobi-like forms. Well, you are probably more used to Jacobi forms. Well, Jacobi-like is just like Jacobi, but you drop the elliptic property.